Inverse issue of dynamics, determination of the elements of the motion of the mechanical system. The inverse issue means that if we have the assigned force, we can find the elements of the motion of the mechanical system. The mechanical point, mechanical body could be. This Article 9H of the book Mechanical Systems, Calculations of the Marine Facilities. We have two exercises. First exercise. Definite material point M of unit mass equal to 1 moves along the horizontal plane. This in the original time moves along the horizontal plane, with the velocity v0 and the action of the force. Force is minus, and it is vector definition of the force vector. Consists of two components, two vector components. This is flat state. A flat state means in the plane coordinate system x0, y, x0, y. The coordinate system. So F material point, the force, the F characteristics. F characterizes assigned in the vector form of the assignment minus in the brackets we have I not a imaginary unit, I just the index of the ort of the abscissa axis, plus j multiplied by cosine t, sine t, cosine t. J is the ort of the ordinate system. At the initial moment of time, initial mean t equal to 0, the force acts on the point m0, and the force is the 0, 1, 0, 1. This is the force, and the force indicated in the definite one figure 9H1A, and the it's minus 1. This is coordinate of the point 0, 0, 1. Coordinate of the point in the initial time moment when the time equal to 0, and this is a force. Force equal minus j directed as magnitude of the force F0 in the initial time moment is as well 1, but because we consider the vector assignment of the force, that is the direction of the force in the units of the orts of the ordinate axis j. The displacement of the point M1 can define by finding integration of the acceleration. So if we have accelerations, and we have accelerations because we have the mass assigned unit mass. So having the force, we can find the acceleration due to the second law of Isaac Newton, as a law that is the force of the inertia in the inertial coordinate system, in which the coordinate system is moving linearly and with the constant velocity of the system or the stationary system, the force or the inertia equal to the product of the mass of the mechanical point, mechanical body, etc., onto the acceleration of this definite one mechanical body. So let's find first the accelerations. Accelerations we can find here. We have as we have the acceleration components sine t and cosine t. This is components of the acceleration with a minus sign on the abscissa axis and the ordinate axis. So we can find the derivative of the velocity is the acceleration. We have this all to assigned, and next we can find the velocity. Velocity is the integral of the projections of the velocity on the abscissa axis minus integral and the integrand. We have the first component minus out of the integral. We can just derive this minus sine t by dt plus c1. C1 is a constant of the integration, and from the next one component minus cosine t, we can find the component of the velocity in projection on ordinate axis equal to minus sine t plus c2. As well, we used the second component of the acceleration. It's cosine, but the minus over the brackets we have. So this is components of the velocities. And next we can find the displacement, the motion of the point M. The motion we can find is we assume that the derivative of the motion by the time is the velocity. Velocity we got previously, velocity we have here. This is the first derivative of the coordinates of the trajectory of the motion of the material point. So we can find the coordinates of the material point at the action of the force as the integral. This is a velocity integral plus c1, etc. So we can find as a sine plus all this cosine. We have sine. The derivative of sine will be cosine. So from the first one magnitude of the velocity, I mean the projection of this axis, we can find that the coordinate of the location of the point on time dependence equal to sine t plus the constant from the first one, decision constant c1 with the variable t plus c3. As well, we can find the having in the account that the velocity component in the projection on ordinate axis dy by dt is equal minus sine. We got it previously as the component projection on the ordinate axis. Here we have mean sine t plus c2. So we can find the ordinate of the location of the point is by the having the integral of the definite one function by dt. We have to separate the variables here and here next to find the integral, and it will be the ordinate of the point cosine t plus c2 multiplied by t plus c4. To find the constants of the integration, we have to use the initial conditions. Initial when the time is equal to t, the location is x0, 0, y0 is 1. This is location of this point, 0, 0 and 1, yes. And besides, we have the components of the velocity. The horizontal component equal to 1 and vertical equal to 0, because a tangential line is a horizontal one, so we only no zero horizontal component of the velocity. Sorry. Then, when we substitute in these definite equations, and in the previous equations here, I can find that the constants all are equal to 0. So we have finally that velocity is cosine t, component on abscissa axis, and the projection coordinates is minus sine t. That is the coordinates sine t and cosine t, which is coordinates of the location of the point independence on time. If we do this left and right side of each equation squared, next we assume that x squared plus y squared, that is the sine t plus squared plus cosine squared t equal to 1. So we can find equal to 1. This means that the trajectory shape of the motion of the point is a circle of unit radius. The force action on the material point is directed radially to center of the circle perpendicular to the velocity. How we can check this? It is understandable that force directed to the center of the curvature, if we derivative of velocity would be 0, but we have to check it first. To do the check, we can find the scalar product of these two forces, because the scalar product of the two vectors is vectors. If the vectors are perpendicular to each other, then the scalar product has to be equal to 0. This is a definition of the scalar vector of the force assigned. This is definition of scalar vector velocity. We, after finding these constants, we can the velocity equate with zero magnitudes here, 0, 0. C1 and C2 is 0, so Vx will be cosine t and Vy will be minus sine t only. And after the substitute the force and the velocity into the equation of the scalar product, we can find that after disclosure of the brackets, we can find that the product scalar equal to 0. That's why we check it that the actual external force is perpendicular to the vector of the velocity. This means that the force is perpendicular to the velocity of normal acceleration the point experiences. No tangential acceleration that it rotates around the definite reference point 0 with a constant velocity, and with a constant angular velocity, and with a constant radius of the curvature, that is the shape of the trajectory is a circle. Second exercise we have in the inverse issue of mechanics, so having the law of the action of the force to find the element of the motion material point. The material point moves along the definite one axis. The material point measures 1 kilo or so, and we have the force acting in the same direction as the material point moves only in one direction along the axis. Definite one axis could be abscissa. It's not is this abscissa axis of the time variation. This is parameter of the time that we assume that we anyway have the point and we have the flat state. Maybe it's not so much important, but it could be in the space, in three-dimensional space, but we have the constant direction of the force application along the definite one abscissa axis. The projection of force onto this abscissa axis is shown on the graph. So first we have force increased immediately to the magnitude of phi0. Within 4 seconds, the force reduces to, this is 4 seconds, to 0. Next increases linearly to the time equal to h for the same level. And next, the force remains 0 after time equal to h seconds. So the issue is to find the velocity of the point and the action of this force when the time will be equal 10 seconds. So we have the linearly intervals of the variation of the magnitude of the acting force. Time intervals of the movement of the material point. The first is time interval from 0 to 4 seconds. The second is interval from of the time of from 4 to 8 seconds. And the third interval is from 8 to 10 seconds, but with no the action of the force. In the first time interval, the value of the velocity of the material point, one can determine that. So, well, not of the velocity, this is value of the force exactly, because to find the velocity, we have to find the acceleration. Next, we have to find the integral of the acceleration, and next we will have the velocity. But this is a value of the force. Finding due to the proportionality of the on the diagram, we have two right-angle triangle. This is force. This is force F0 at 0 time. At the time to 4, we have the 0 magnitude, and the time equal to t, we have the force F. So 4 minus t, this is a leg of this one internal right-angle triangle, and the 4 is the leg of the big triangle. So in this definite one proportion, we can find that the amplitude value of the force corresponding to the initial moment of time 0 equals to 10, then we can find that the force at any definite time moment within the interval from 0 to 4 seconds will be 10 minus 5 divided by 2 multiplied by theta time within the interval from 0 to 4. And since the mass is equal to 1 kilo, we can find the acceleration equal to the force. So acceleration nominally, formally will be equal to 10 minus 5 divided by 2 by multiplied by t meters per square second. This is the acceleration. And next we can find the velocity. Velocity we can find as we will take the integral of the acceleration by time. So we will find that the velocity is minus 5 divided by 4 at, excuse me, this will be the velocity within the fourth segment of time from 0 to 4. And minus 5 divided by 4 multiplied by t times squared plus 10 by t plus c1 meters per second. So, and when finding the integration constant, the initial condition is used. At time equal to 0, the velocity equal to 0, then we can find that at t, if is 0, 0, the velocity is 0, so c1 have to be equal to 0. And at the end of the first time interval, the velocity, when we have this 0, the velocity next only to first summons remains in the decision, and considering this definite initial conditions. And we have these two summons for finding the velocity after the substitute of the 4. 4 is the time end of the first segment, of the first linearity dependent segment. To 4 next will be from 4 to h. So, but at the end of the first segment, at time equal to 4, we have the velocity of 20 meters per second. The second time, excuse me, the second time interval motion from 4 to 8 seconds, the value of the velocity of them, we can find determining the proportion in the second one triangle. So we have on the diagram two similar triangles. But they are of the proportional sizes. Time assigned definite time t, but this leg corresponds to this force as this big one leg from 4 to h, like as the time correspond to the next one force if 0. And having this proportion, we can find that the acceleration is by this definite one formula, f equal to f0 divided by 4. This comes of this proportion, f divided by 4 multiplied by time minus initial force equal to 5 divided by 2 multiplied by t minus 10 meter per square second. This is a meter per square second because actually this nominally is the acceleration, but it is equal to the force as we have the mass of this body equal to 1 kilo. So, and excuse me, this is not the value of the velocity as well as in the previous one time, just a mistake in the description, is the value of the force, because due to the diagram we have the value of the force, but not the velocity. Velocity is subject to find. So this is a value of the force. Next, we can find that the velocity by the integration of this equation of dependence of the acceleration. And having that, we can find that the velocity on the second segment from 4 to 8 seconds will be 5 divided by 4 multiplied t squared minus 10 by t plus c2. So we have to find the c2, what is equal to the c2. The c2 we can find as from the initial condition that at time equal to 4 seconds, we have the velocity 20. 20 is the final magnitude of the velocity for the first segment of time when we consider from time from 0 to 4 seconds. So that time equal to 4 seconds, the velocity will be 20. Therefore, this velocity is the initial magnitude of the velocity for the second segment of time from 4 to 8. When we substitute this velocity 20 seconds will be, excuse me, 20 meters per second. Instead of time, we substitute 4 seconds. So after the substitute of all of that, we can find that C2 is equal to C2, yeah. This is not C1. C1, this have to be C2. C2 have to be, it is 40 meters per second. Well, yeah, exactly 40. Just one correction, the description, this have to be C2 and here C2. And the functional dependence on time of velocity of material point in the second time interval motion is has the form 40 as a C2 here. Substitute C2 and the here is C2. It is at the end of the second interval, the velocity at the end, when we set next to this formula got for the second interval from of time from 4 to 8 seconds after substitute of the time equal to the end of the interval, that is 8 seconds, then we will have the velocity is 40 meters per second. The velocity material point at the third motion interval from 8 to 10 seconds is constant because the force along the acting on the point equal to 0. Then the acceleration at the third time interval from 8 to 10, the acceleration will be 0, 2, and the acceleration will be 0. The velocity will not change it at the third interval of time of the action of the force onto the moving point onto them. So the velocity at the time equal to h, 40 meters per second, is the same as the velocity at time 10 seconds, 40 meters. That is assigned to find what is the velocity when time is of the action of the force is equal to 10 seconds. H is the velocity is 40 meters per second. Questions and comments. Finding projections of velocity displacement by of the point by integration parametric functions. That is the dependencies of the parameter of projections onto the coordinate axis of force action on the body, substitution of initial conditions, determination of the integration constant. For decision of the second issue of dynamics, that is finding the elements of the motion of the material point when assigned the lowers of the action of the external efforts like external forces and external moments caused could be in the dynamics and the accelerations, translational acceleration, angular accelerations. So before the second issue, that is when assigned these external efforts the forces and moments. So we can find the accelerations if we have the inertial characteristics of the elements mechanical system of the material point. It could be mass characteristics or moments of the inertia characteristics of the mechanical system element. So having these inertial characteristics and external forces, we can find the accelerations, the linear acceleration, or it could be the angular acceleration of the elements mechanical system, the material points, or the other elements of mechanical systems. And to find the elements of the motion, like velocity or the coordinates of the element mechanical system, we just can use the differential dependencies of the elements of the motion, like the dependencies of the acceleration, velocity, I mean linear or angular, and the coordinates, the same linear or angular, we can find by the integration of the acceleration first. 9.2 determination of the coordinate form of trajectory of the point by excluding the time parameter from the found the parametric functions of the point coordinates depending on time. If we have the parametric dependencies of coordinates, for example, abscissa coordinate and ordinate coordinate in the flat state, then we can derive time parameter if we have the parametric dependencies of time from one of these two coordinates and have this time parameter definition by the coordinate definite one, maybe abscissa or ordinate. We can next substitute this time parameter got into the another component definition of the coordinate. Instead of the parameter, we can substitute derived magnitude of the parameter from the independence of the coordinate of the another one coordinate. So then we can exclude the time parameter from the mathematical equations, and we will have the the shape of the trajectory of the motion of the material point or the element of the mechanical system. It depends on what is element mechanical system. Could be the point or could be mechanical body, etc. 9H3, the direction of the force acting on a material point, the angle of direction of the force relative to the tangent, to the trajectory of the point, determined by the criteria that the scalar product of the force vector on the vector of the velocity of the point is zero. We can do that as the scalar product equal to the product of two magnitudes of two vectors by the cosine of the angle between these two vectors. Then if the product is zero, that is if each or any of these two vectors is zero or the cosine is zero. If this magnitudes of each of two vectors is not zero, then the cosine of the angle is to be zero. That means that the vectors are perpendicular to each other. We can check this by the use of the scalar product of the vectors, for example, the vector of the velocity and acceleration, to decide is the acceleration perpendicular to the direction of the motion of the material point, the direction of the velocity, or etc. 9H4 finding time the duration for the point to move the specified distance under the influence of the force act, integrating the acceleration function twice, taking into account the initial conditions. Yes, as usual, because if we have the assigned the external efforts, could be forces or the moments acting on the elemental system, in particular on the material point with the defined mass or assigned mass. Then we can find the acceleration, and we can use next derivative dependencies of the acceleration, velocity, and the coordinate or the location of the point. So the sequence, the velocity is the first derivative of the coordinate by time, and the component of the acceleration is the first derivative of the velocity, or the second derivative of the coordinate of the location of the element mechanical system, in particular the material point. 985, the determination of the elements of motion of material point, the acceleration, velocity, and displacement, when a variable over time intervals force act on the point. We can consider the motion of the point separately for each interval of time of the assignment of dependence of force on time. So if the force is assigned, or any other effort, could be the moment of the rotation, if this effort assigned by the intervals of time, then we can consider this consequently the motion of the point within the time intervals. And we have to adopt the initial conditions for each interval as a final magnitude of the elements of the motion for the previous one interval, considering the action of the forces or moments at each next interval. Thank you.